All right. So good morning, and to our friends joining us abroad, good evening. Welcome to Mirage Talks. Today we welcome Professor from the Weizmann Institute to speak to us on how to train the Schroeder cat in quantum computing. Roee Ozeri, thank you so much for joining us today. Welcome.
Thank you very much, Christy. So yeah, good morning, everyone, and good evening for those of you who are on this side of the Atlantic. So my good friend Eli Tiomkin asked me to attend this meeting and give a little presentation about quantum computing, which is really the subject of my research at the Weizmann Institute of Science, and it's my pleasure to do so. So thanks again for inviting me, and thanks for taking the time. So what you see here in this picture is an image of 8 trapped ions. Each point you see here, do you see my cursor? Is that good?
Yes.
Yes.
Good.
It's all good.
So each point, each dot you see here is a single atom, and we use these atoms as quantum bits. So this is, if you like, a quantum byte that we have in our lab. And what you see below is an image of a trap we're building for a 50-qubit quantum computer, also in our lab. And I'm sure many of you, maybe most of you, heard about quantum computing in the last few years. Quantum computing has certainly been in the news as a new paradigm, as a hot topic and a new paradigm for computing. About a year and a half ago, Google announced that with a quantum computer of 53 qubits, they were able to perform for the first time carry out a calculation that could not have been done using regular classical computers. So the first demonstration of quantum advantage was performed by Google about a year and a half ago, and that really caught the attention of the public eye. I think it's well understood that quantum computing, if quantum computers would actually mature to a viable large-scale technology, that would be a truly transformative and disruptive technology and a strategic asset. In fact, this is an article by Forbes magazine from 2019 claiming that the quantum race is probably the most important strategic technological race between the US and China today. So I think the importance and the prospects of quantum computing as disruptive technology are already acknowledged. And the big industries, the big technology, the big information technology industries, the giants like IBM, or Google, or Amazon, or Microsoft, as well as Intel, all today harbor in-house development of quantum computing. So I think, with everyone knowing that quantum computing is an important technology, maybe it's worthwhile spending a little bit of time trying to understand what quantum computers really are. So in order to be able to do that, we have 2 tasks at hand. The first is really to tell you what quantum mechanics is, so to give you a crash course in quantum mechanics. And then after we all understand quantum mechanics, tell you a little bit what quantum mechanics has to do with computing, and why is the physical theory relevant when we try to think of computation. So let's begin. So what is quantum physics? So in order to explain what quantum physics is, maybe I should start with trying to explain what is physics. So physics really, and to explain what physics is, I'll use a metaphor that comes from the world of computing, which is fitting. So, we all work with computers all the time. And when we work with computers, we work with operating systems. So for example, if you work with PCs, you would use Windows. If you work with other computers, you would use other operating systems. But the idea or the principle behind an operating system is that it doesn't matter which program you use. And if you use a computer, you use very many different types of softwares. It doesn't matter which software you use. Each software you use has to respect the rules set forth by the operating system. And what we do as physicists, we're trying to find the operating system of the universe. We're trying to find the set of laws, the smallest group of laws that really dictate the behavior of any phenomena in the universe. So the same way that the operating system of the computer really dictates a certain set of laws that has to be respected by any software that you'll use in this computer, a good physics theory, or the ultimate physics theory, would be a physics theory that would really describe any phenomena in the universe. Doesn't matter how big this phenomena is, how small this phenomena is, how fast, how slow. All phenomena in the universe should obey the laws of physics. So what we're really trying to come up with as physicists, our core mission is to come up with a theory of everything. A theory that would explain all phenomena in nature, and it doesn't matter if these phenomena are as large as a galaxy or as small as a single atom or the size of a person or a soccer ball. It doesn't matter. All these phenomena, large or small, should obey the law of physics. And that is a truly difficult challenge, because let's look, for example, on length scales. If you look at all the length scales in the universe, there are many, many orders of magnitudes of different phenomena that we're familiar with in the universe. So, for example, an average person would be, roughly the size of 1.5 meters or 2 meters. Earth radius is roughly here. And if you look at the Earth-Sun distance, it'll be here. What you see here, by the way, is what we call a logarithmic scale ruler. This is a ruler where the difference between, if you look at different bars on the ruler, they do not represent a constant difference, but rather a constant ratio. So the ratio between this bar and this bar would be 10,000, 10 to the 4. The ratio between this bar and this bar again would be 10 to the 4, would be 10,000. So if I look at the different scales in the universe, again, if an average person is here, an Earth radius is here, the Earth-Sun distance would be here, the Milky Way galaxy diameter would be over here, and the size of the observable universe, perhaps the largest object we can think of, is roughly 10 to the 29 meters, so 1 with 29 zeros beyond it. If I look at smaller phenomena, the wavelength of visible light is roughly 1/1,000,000th of a meter right here. The size of an atom is about 10 to the minus 10 meters, so 1/10 of 1/1000,000th of a meter. A proton is about 10 to the minus 15 meter. And Planck's length, which is what we believe is, if you like, the pixel size of space, the smallest length we can think of, is roughly 10 to the minus 35 meters. So if I look at the different scales I have in the universe, I have almost 70 orders of magnitude. So if you like, one with 70 zeros behind it, of different sizes, phenomena with different sizes in the universe. So if I'm looking for a single physical theory that would describe all these phenomena, it's a very difficult task. And in fact, we have failed to do so. So if you look at phenomena which is about our size, if you remember, an average person is about 1 meter. So phenomena which is, in our comfort zone, we have one set of physical laws that were discovered 300 or 400 years ago by Isaac Newton, and we call that Newton's mechanics. If we look at much larger phenomena like galaxies or clusters of galaxies or the entire universe, we see that our operating system changes. We no longer can use Newtonian mechanics. If we look at these huge, massive objects, the theory, the physics that we need to use is general relativity, a theory that was discovered about 100 years ago by Albert Einstein. But if we dive into the microscopic world, we dive into the world of atoms or molecules and electrons and protons, again, we see that the operating system changes. The set of laws that we need to use when we look at the microscopic scale, and that's a different type of physics, a different operating system, is called quantum mechanics. So the take-home message that I'd like you to leave this lecture from, or one of the first take-home message, is that quantum physics is the physics of small things, atoms, electrons. If you dive into the small particles out of which all of us are made, we see that when we go to the microscopic world, the physics that we need to use changes. Instead of using Newton's mechanics, we need to use quantum mechanics. So quantum mechanics is the physics of the microscopic world. So now that we all understand what quantum mechanics is, so we can now ask the question of how are the laws of quantum mechanics different than the laws of physics that we are familiar with in the macroscopic scale. And again, so in other words, what is the difference between a sphere, which is of a radius of maybe 20 centimeters, a soccer ball, then a very similar sphere? Actually, often we represent atoms as these little solar systems. In practice, most atoms look like perfect spheres, at least when they're not agitated, when they're not excited. So what is the difference between this sphere and this sphere? The main difference between them is that this one is about 10 billion times smaller than this one. But what is the difference in terms of the physics? What is the difference in terms of the laws of the operating system, which dictates the behavior of this small sphere as compared to this small sphere? And again, to explain this difference, I'll use a metaphor. So in the world of macroscopic objects, in the world of in our world, there's a very obvious fact, and the fact is the following, and I'll explain it using this example. This is a picture of myself and my family in a trip in the Austrian Alps, and what you see here is a picture of me in the lab, and I like spending time with my family, in trips. I like being in the lab, and here's the problem: I can't do both at the same time. And this is really the result of an obvious fact. We can only exist in a single reality at any given time. I can only be in one place at any given time. I can either be in the Austrian Alps or be in the lab. I can't be at both places at the same time. Now, if you look at quantum mechanical particles, if you look at atoms or electrons, you'll see that according to the laws of quantum mechanics, atoms can actually exist in several places simultaneously. And this is a very surprising fact. And let me give you a little explanation of how we think about existing in multiple locations simultaneously. So if we look at the world, we often divide phenomena in two very distinct ways. One way that we describe phenomena or objects, if you like, we describe them as particles. So here you see a picture of a few pebbles, and each one of these pebbles, we think of these pebbles as particles. Particles have the trait that we think of them as locals. Particles can either be in one location or another location. Particles also add up in a very simple way. If I take one particle and add another particle to it, I get two particles. If I add another particle, I get three particles. Particles are very simple objects. A different type of way to describe phenomena in the world, a different object, if you like, is that of waves. Waves are very different than particles. Waves, for example, are very non-local. They're not in a given position. Waves are spread over space. What you see here is a picture of the wave that is generated by dropping one of these pebbles into a pool of water. And when you do that, you see circles, a circular wave, which is expanding outwards. So as you can see, the wave is not localized. It's really spread across, across this pool. Another peculiar notion about waves is that waves add up in a very non-simple way. Waves interfere. What do I mean by that? If I take two waves, and one way I think of a wave is as this periodic perturbation, a mountain followed by a valley, then followed by a mountain, and so forth, and I add another wave to it, they can meet in a way that a mountain would meet a mountain and a valley would meet a valley, and then I'll get a wave which is twice as high and then twice as low. But I can also make waves meet each other in a way where a mountain meets a valley and a valley meets a mountain, and this way the mountain annihilates or nulls the valley and the valley nulls the mountain, and the waves actually nullify each other. So instead of getting constructive interference, which generates a larger waves, waves can also interfere destructively and actually annihilate each other. So waves are very different than particles. And we're very used to wave-like phenomena. You see here an image of tide coming in from the Atlantic into the Mediterranean through the Gibraltar Narrows, and you see that waves, even when I try to localize them through the narrow, they diffract in nice diffraction rings into the Mediterranean. You can also, this is an image taken, both these images are taken from the space station. What you see here are waves that are reflected from the shores of this little group of islands called the islands of Scilly, a little south of England. And you see that the reflection of waves from the island's shore forms an interference pattern here. So waves are very ubiquitous. We see them everywhere in nature. And what quantum mechanics tells us is that atoms, which we often think of as particles, behave like waves. What you see here, again, are images from our lab at the Weizmann Institute of Science. You see an image of an atomic cloud. So this is a very cold gas made out of atoms, and the atoms here interfere with each other. What you see here are interference fringes. The dark areas are areas where the atomic wave destructively interfered, and I don't see any wave, I don't see any atoms here. The white areas are areas where the atomic wave constructively interfered, and I see many, many atoms. So quantum particles behave like waves. Because they behave like waves, they can be in multiple locations simultaneously. Unlike us, we don't behave like waves, we behave like particles. This is here, I don't know how many of you have a little bit of experience in optical technology, but I think this example would be important later or helpful later when we speak about computers. If I take a wave, let's say in this example it's an optical wave, let's say a laser beam, I can split it into two waves. And for a wave, it's not a problem. A wave is not necessarily local. I can take a wave and then with this semi-transparent, semi-reflective mirror that I put in its way, part of the wave would reflect in one direction, part of the wave would transmit. I can then put mirrors and make the waves join each other again on a semi-transparent mirror and window, and then they can exit either through port A or through port B. Now, I can ask the question of whether the wave went through path 0 or path 1. The answer is the wave is unlocalized. The wave went both through 1 and through 0. I can also ask the question, did the wave exit through port A or port B? The answer would be that it really depends. The wave can exit both through port A and through port B. It really depends on the phase difference between these two paths. In other words, it'll be determined by whether on this mirror here, a mountain meets a mountain and a valley meets a valley, or a mountain meets a valley and a valley meets a mountain. That would determine whether the wave, the light, the laser light would exit through port A or through port B. So waves are much more complex than particles. So because we think of quantum particles or quantum objects, atoms, electrons, molecules, as waves, we can imagine or we actually describe them as existing in several places simultaneously. And it's not just place, it's actually any physical reality that we think of. These quantum particles can exist in a wave which is spread over all these realities. So for example, I can think of an atom that can be red or yellow. A quantum atom can be both red and yellow simultaneously. I can think of the atom as having a little magnet attached to it. We're used to thinking of magnets as pointing either north or south. Quantum magnets, meaning magnets that are attached to atoms, can point both north and south simultaneously. This is a very confusing notion to come to terms with. We use it, the term that we use for it in physics is the superposition principle, but what we really mean when we say the superposition principle is that quantum particles can exist in multiple realities at the same time. This was an idea that was very difficult for physicists 100 years ago when quantum mechanics just started to be developed, to come to terms with. Very important scientists like Albert Einstein or Erwin Schrödinger, who were the fathers of quantum mechanics, had significant difficulty to come to terms with these ideas. Today we know that we don't have a better way of describing the microscopic world, and I think that by now the physics community has accepted this view of nature, as difficult and counterintuitive as it is. And this is really the second take-home message I would like you to take from this talk. And this is the take-home message that atoms or any quantum particle can exist in multiple realities simultaneously. Good, so now that we're all experts on quantum mechanics, we can ask ourselves, how are the laws of quantum mechanics, how is a physical theory really related to computing? And I think to understand the connection, one thing we have to keep in mind is that computers, we used to thinking about computers in very abstract ways. We think of computers as, as devices that get these files, which have megabytes of information, of gigabytes of information, and then do all sorts of logical and mathematical operations on these files of information. But something we often forget is that these computers are actually machines. They're machines. They're built out of matter. And when we think of a movie, several gigabytes of information, we have to keep in mind that several gigabytes of information is several tens of billions of objects that represents bits, that represent either 0 or 1, that actually flow from one place to another. If we want to download a movie, we actually have to receive a few tens of billions of physical objects. Very often these would be pulses of light. These can be electronic, so bunches of electrons, but at the end of the day, these are physical objects that flow into our computer. And when our computer stores information, when we have hard disks or flash memories on our computers, we have to keep in mind that if these memories store gigabytes of information, these memories actually store tens of billions of physical objects. Computers are physical machines, and as physical machines, they should obey the laws of physics. And now comes the question, the laws of which physics? We just learned that there is no one theory that describes all phenomena in the universe. When we're speaking about objects our size, we have to use Newton's laws, Newton's mechanics. If we speak about very small things, we need to use the laws of quantum physics. So when we think of computers, which set of laws do we need to use? Do we need to use classical, regular Newtonian mechanics? Do we need to use quantum mechanics? And we know that computers today are being built by smaller and smaller objects. And as smaller and smaller objects, we get more and more reasons to use the laws of quantum mechanics as we think of computers and as machines. And if we do so, if we use quantum mechanics to describe the machine work of computers, we can ask the question of how different would be the operation of these computers, of these quantum computers, from the operation of classical computers. And the first person to point out that perhaps computers that obey the laws of quantum mechanics would be more powerful than regular classical computers is this handsome guy here. His name was Richard Feynman. He was an American physicist at Caltech. And Feynman's argument was relatively simple. Feynman said, gave the following conjecture. He said, look, think of a single bit that we store in a regular computer. A single bit is a physical device which has two states. One state represents 0. The other state would represent 1. If we think of a quantum bit would be a quantum system with two states, but now that quantum bit can be simultaneously in 0 and in 1. So what happens when we think of 2 bits? 2 regular bits are 2 switches. Each one of these switches has 2 states. These 2 bits have 4 possible logical states: 0, 0, 0, 1, 1, 0, and 1, 1. What if we think of 3 bits? 3 bits, each has 2 states, and these 3 bits would have 8 different logical states they can be in. If we think of 2 quantum bits, these 2 quantum bits can be in all 4 states simultaneously. If we think of 3 quantum bits, they can be in all 8 different states simultaneously. The law here is really 2 to the power of the number of bits that we use. And if we think of 100 bits, and remember on your computers today, use computers with billions of bits. If we think of 100 bits can be in 2 to the 100 different possibilities. 2 to the 100 is a number which is larger than the total number of atoms in the universe. If we would ask our regular classical computer to go over all 2 to the 100 different possibilities, it would never finish this calculation even in the lifetime of the universe. A quantum computer, on the other hand, can be 100 quantum bits, can be in all 2 to the 100 different possibilities simultaneously. And this is a huge, an exponential advantage over regular computers. It's an exponential advantage if we know how to use it. So one way, and this is again an example for those of you who are feel a little more comfortable with ideas that come from the world of optics. If we spoke before about an interferometer, device that splits a single laser beam into 2 different paths, a quantum computer is really like an interferometer, but an interferometer with 2 to the 100 different paths. If this quantum computer has 100 quantum bits in its register, it's a highly complicated device. If we want the quantum computer to work, we need all these different paths to interfere the right way such that all the energy would exit this interferometer from a single exit port. That would be the outcome of our calculation. But if we want that to happen, we actually need to make sure that the phase difference between the different paths, in other words, that all these waves would go to their exit ports in a way that a mountain would meet a valley or a valley would meet a mountain and so on. And this way, all the energy would exit this quantum computer in the right port. It's a very difficult task to build this computer, but if we can do so, we can get a computer that is exponentially more powerful than any regular computer that we have today. So again, by trying to simplify things, if I look at the strongest computers that we have today, this is the Summit computer, which is, as far as I know, that's at least the publicly known. It's the strongest supercomputer that we have today. It's not a supercomputer because it uses one very, very fast processor. It's a supercomputer because it has tens of thousands of regular processors that are operating in parallel. It's a cluster of processors. That's why it's the strongest computer on Earth today. A quantum computer is not a parallel computer in the sense that it doesn't have a cluster of processors working in parallel. It has a single processor, but that single processor computes in multiple realities in parallel. That's the reason a quantum computer is in principle more efficient than a regular computer. So, in the 30 years that passed since people came up with this notion of quantum computer, people came up with many different algorithms that demonstrate the power of quantum computers. And I'm not going to give you these algorithms. I'll just say that one of the algorithms here, this is the factoring algorithm. The factoring algorithm is an algorithm that takes a very large number and breaks it into the product of the prime number product that compose this number. This may sound as a boring, mundane task, which would only interest mathematicians. In fact, this is the algorithm that allows us, the fact that solving this algorithm is difficult is what allows us to send information, encrypted information, through the internet. If one would come up with a computational ability to perform this task in an efficient way, this person would be able to break the strongest encryption that is used today, both in the civil as well as the defense world. So this is really, in many ways, a holy grail for quantum computers. Again, for those of you who are versed with computational complexity and the world of computer science, we know that there are some problems that we can solve with polynomial complexity. There is a class of problems that we can verify that the solution to the problem is correct with polynomial difficulty. We now believe that quantum computers are in principle stronger than regular computers in the sense that they can solve with polynomial difficulty problems that regular computers can't. So I know this statement is a bit technical, but again, for those of you who are familiar with computer science, that's a useful statement. So what would be the applications of quantum computing? Quantum computers, actually there are many applications. To start with, quantum computers would be very good in trying to simulate the way quantum systems behave. For the very same reason that quantum computers are in principle stronger than classical computers cannot calculate how a quantum computer would behave. In fact, they would not be able to calculate the way a quantum system would behave if that quantum system has a sufficient number of atoms in it, for example. So classical computers can't really calculate how big molecules behave. For that very reason, classical computers can't calculate how a chemical reaction would happen. So today, the way we perform chemistry is really by trial and error and coming up with ad hoc, if you like, heuristic rules. It's a little bit like cooking. We know we have statistical arguments, we have thermodynamical arguments, but we can't calculate the way complicated chemical reactions would happen. With a quantum computer, we would be able to calculate the way chemistry works. And in terms of material design, in terms of material engineering, this would be a transformative revolution. Optimization problems that comes from the world of optimizing investment portfolios or optimizing logistics. Many of these optimization problems in order to find an optimal solution, have to go over, survey an exponential number of different options in order to find the optimal option. Quantum computing would be able to solve these problems probably much more efficiently. by actually serving all these options in parallel. Machine learning, again, in many ways is an optimization problem. It's trying to optimize output to different inputs. Machine learning would benefit from quantum computers. We already mentioned cryptography. You would be able to break very strong codes using quantum computers. So quantum computers would have a lot of many applications, both in the civil world as well as defense. And that's why we see today huge investments in trying to realize quantum computers. So now that we understand what quantum computers are, we can ask the question, how do we build a quantum computer? And I think that unlike CMOS electronics today, where there's really a single technological solution that really won the entire pot. You know, today, silicon electronics and silicon is really the way people fabricate transistors and electronics. And even if someone would find a better material, so much was invested in silicon foundries and silicon technology that today it doesn't make any sense to try and engineer a different way to go about regular electronics. In the world of quantum computing, the race is still ongoing. There's no single technology that proved to be better than the other. So the race is still on to find the best technology. And I think there's a couple of categories that people follow when trying to build a quantum computer. The basic rule is that you try to find, or you find systems that are small enough and quantum enough by nature, for example, single atoms. And then you build a quantum computer by adding more and more of these systems to each other and going from a single qubit to a larger and larger arrays of qubits. And people follow two different categories. One category is using natural qubits, like atoms. These are nature-made small systems that obey the laws of quantum mechanics. A different trajectory that people take is that of engineered qubits. So if you like, electronic circuits that are small enough and cold enough in order to behave quantum mechanically. So I'm just going to give a few examples for technologies that people use today. This technology here is the technology that I use in my lab, technology of trapped ion qubits. Again, what you see here are 8 trapped ions. They actually hover in mid-nothing. They hover in space, in vacuum. They're held by electric fields, and these electric fields are generated by electrodes that are fabricated on a chip. So like regular computers, we use chips. These chips are the chips of the electrodes. The electrodes apply electric voltages, and above these chips, inside these, if you like, virtual boxes, these atoms are traps, and we use each one of these atoms as a quantum bit. What you see here is a chain of 50 such qubits, and it's not to scale. The chain here is much smaller than the chip, and it hovers at a very small height, a very small height above the chip surface. This is a different example for a technology. These are quantum dot qubits. Quantum dot qubits are qubits that are made by fabricating artificial atoms, if you like. What people do here is they build very small devices, hundreds of nanometers, smaller than 1 micron. These electrodes generate electric fields that again build boxes, but not boxes for ions that hover above the chip surface, but rather the electrons that are in the metal below the electrodes. This way, it's a box for electrons, and in many ways, it behaves like a single atom. Australia has a very large effort of trying to realize quantum computers using quantum dots. Intel is investing a lot of money in building these, and I think one of the reasons there is that these are consistent with silicon technology. Another very successful approach, perhaps the most abundant approach today in the industry, is that of using superconducting circuits, superconducting qubits. These are electric circuits that are made out of superconducting materials. Superconducting materials are materials that do not have any resistance. And these circuits, again, behave very much like artificial atoms. If you want to work with these qubits, by the way, both these superconducting qubits as well as the previous qubits, the quantum dot qubits, you have to work at extremely low temperatures, about a 1,000th of a degree above, or 1/100th of a degree above absolute zero temperature. Another approach is using photons, particles of light as qubits. This technology is maybe slightly similar to the interferometer that I've shown you before. Again, this technology is consistent with silicon. In this case, it's silicon photonics. So the way people go about building quantum computers using photons is by building silicon chips and then having silicon oxide waveguides. So if you like, optical fibers integrated into the chip surface. In this way, build quantum computers that are using photons as qubits. A startup which attracted huge investments, close to $500 million in California, called PsiQuantum, is one of the leaders of this technology. Today, there's large attention by governments into making sure that their countries harbor quantum computing initiatives. The US, about a year and a half ago, declared $1.25 almost billion National Quantum Initiative. Europe inaugurated its €1 billion quantum flagship a couple of years ago. Even in Israel, for those of you who read Hebrew, very recently the government allocated 1.2 billion shekel in order to establish quantum computing research and industry in Israel. So I think all governments are very aware of the strategic opportunities and threats that quantum computing holds, and therefore are investing large sums of money in this direction. The private sector has followed very quickly. Today, as I said, all the big companies, all the big tech giants like Google, like Amazon, like Microsoft, like Intel are invested in quantum computing. What I've done here is I sort of put a short list of some of the players, the industrial players in quantum computing under different technologies: superconducting circuits, trapped ions, photons, silicon quantum dots, topological qubits, which is a type of technology I did not describe, which Microsoft is leading. All these are attracting large investments. IonQ, which is a trapped ion startup from Maryland, last week announced that it's going public through a SPAC, which being a scientist and not an investor, I'm not quite sure what it means, but I know that together they're actually going public for $2 billion, which is a huge investment. You also notice that some of these players are startups and they get investments from venture capitals. I think, though, that still today the largest investments in this field come from strategic investors like Google, like Intel, like IBM, like Microsoft, who are not looking for fast return in the next few years, but rather are strategically interested in having the know-how and having their foot in the door, if you like, of quantum computing. Quantum computers today are pretty small in the number of qubits that they harbor. So, as I said, I think that the largest demonstration so far, that was the first demonstration of a computation that was done using a quantum computer and that no classical computer could have performed, was performed by Google. with a quantum computer of 53 qubits. 53 qubits is a small number of qubits, as if you compare that to the number of bits that you have on your computers, again, billions. Nevertheless, these 53 qubits were able to carry out a calculation that even the Summit, the IBM Summit, could not complete in reasonable time. And the reason is that 53 is a small number, but 2 to the 53, 2 to the power of 53, which is the advantage of that quantum computer, is a very, very, very big number. So while quantum computers are now of modest size in terms of the number of the qubits that they accommodate, they're actually not very small in size at all. This is a picture of IBM Q. It's a 20 qubit machine in New York. And that 20 qubit machine, as you can see, is almost the size of a room. What you see here are the dilution fridges, which cool down these superconducting chips to about 100th of a degree above absolute zero. What you see here is the first and only quantum computer in Israel. It's the Weizmann Institute quantum computer using trapped ion technology. So again, 8 qubits. But these 8 qubits are accommodated in this relatively large machine. So again, these quantum computers are not likely to fit inside your smartphone anytime soon. And that's true, but keep in mind that this is actually how the electronic computer looked like, not too long ago, less than 70 years ago. This is a picture of the Weizsäck, the Weizmann Institute automatic computer. This was the first computer in Israel, built in 1954 by Chaim Pekaris at the Weizmann Institute. If you guys come and visit the Weizmann Institute, and I encourage you to do that, you can still see it, this computer portrayed in our computer science faculty. And this computer, which is almost the size of a room, had a 40-bit input. And it was composed out of a few thousand vacuum tubes. So within 70 years, machines which are probably almost a billion-fold larger in terms of the number of bits that they have do fit inside your smartphone. So if we judge from history, we shouldn't be discouraged by the fact that quantum computers today have a small number of qubits and are very large. I personally believe that the future of quantum computers is bright, and that it would lead to a disruptive revolution in computing and computer science and technology at large. So that's it. With that, I conclude, and if you have questions, I'll be happy to answer.
Can I have a question, please?
Sure, yeah.
Hi. So thank you for the lecture. It was very interesting. And I wonder, you explained the history of the PC as we know it today, or smartphone as we know it today, comparing to the first computer built in Israel about 70 years ago. So how far you think the quantum computer will be commercial, you believe? Like it's 10 years far, 20 years far? Commercial, I mean, it's not need to be in a smartphone yet, but like a commercial usage, any other commercial usage.
So, well, quantum computers are already commercial.
No, commercial user, I mean by the public, not about like specific labs or scientists.
No, I mean by the public. And I think the first approach, and that's the approach which is taken by most players in this field, is not to build a quantum computer that would be a commodity that you'll buy and you'll put in your house, but rather building machines that are essential and provide cloud services. It makes a lot of sense, both in terms of the complexity of that machine, as well as in terms of the way the computing world, at least one of the vectors towards which the computing world is advancing anyway, in particular that of HPC. And quantum computing is not it's not computing in the sense that it's part of high performance computing, if you like. Quantum computers are very likely to serve as accelerator cores inside HPC machine, high performance computing. And And these high performance computing are very often used in the cloud. Even today, you can log into IBM Q and run quantum computing, quantum algorithms on their quantum computer. You can use Amazon Bracket Service, which actually sells you runtime on different quantum computing platforms, actually on 3 different vendors, D-Wave, IonQ, and Rigetti, actually using quantum computers of 3 different technologies. So already today you can buy cloud time and run algorithms on quantum computers. I believe in Amazon Bracket, it's of the order of 1 cent per run, per repetition.
So you mean the quantum computing is starting to replace, like, let's say, the big servers, the cloud servers?
I think that it's more, I don't know if it's replacing servers today. I think that quantum computing and using quantum computers requires a very special kind of algorithmic tools. You really have to, it's not just running regular software on quantum computers. You need to run quantum software on quantum computers, and quantum software is different. I think that quantum computers are not at the stage where they can run important algorithms more efficiently than regular computers. I think it'll still take time until quantum computers are very useful. I think today most users are using quantum computers not because these computers can solve problems that they can't solve otherwise, but mostly because they want to train themselves with quantum algorithms and the way quantum computers should be run, and trying to prepare themselves to 5 or 10 years from now, where these computers are actually an important technology.
Thanks. I have a question too, if you have okay?
Sure, yeah.
First of all, I want to say, Roee, this is a great talk, and it stands out. I just left a comment. I'm wondering if you could reply with your email address. If this is recorded, I'd like to post it on a site that I have called Quantum Curious. It's on the chat. And the purpose of the site is just to bring together learning resources, but focused only on beginners.
Sure, so I'm sending
your talk
my...
stands out because it's about as gentle an intro as I've seen. Those are great slides. Most of the talk for beginners, they just cut and paste, technical looking slides, and they don't get down to the attention that you did. So it's an outstanding job in that area. I wanted to post it. If this is recorded on my site, I think a lot of people would benefit from it.
Well, thank you very much, Nathan. You're welcome to post it, and I sent my email address on the chat. So.
Oh, great. I'll follow up with you in the next day or two. Well done. Thanks. And then a technical question on the IonQ, and I also mentioned it too. It's amazing that a pure play quantum company got listed publicly on All Places NYSE, a very, high-end market. And 3 years ago, you hardly heard of quantum. So that's an extraordinary, the timing of your talk is also good. And the industry needs a lot of players. One of the big challenges it has is not only technical, but this was a New York Times article. It's on that Quantum Curious site. There's a link to it. They need something like 35,000 participants in the next 5 years, and they've only got 3,000 at max in the world. So it bodes really well, especially for people just out of college. And
I agree.
It's important STEM people now. It's maturing at a point now where you need the edge folks. You need the marketing people. You need the the public relations people. You need to get the word out, and that's
I
a
agree.
very
I think
encouraging sign.
One of the biggest challenges we have in this field is that of manpower. I think there's just not enough engineers who understand quantum mechanics. I was part of a committee that designed the quantum program for the higher education system in Israel. And we realized that what we need to do, and we need to do fast, is train more, not just the physicists, because the number of people who would take physics for graduate school, that's too small of a number to really, to be the train that would take this technology forward. We need the engineers. That means that, and we need the computer scientists, and we understand that we need to include quantum mechanics and quantum physics education into the curriculum of engineers and computer scientists, such that there'll be sufficient number of people who are, who know quantum mechanics to really take on this technology.
Yeah, I totally agree. And fortunately, the science behind it, the math, it's challenging, but it's not impossible because it's linear algebra. So it's linear and it's algebra. So it's basically comprehensible if you're disciplined and give it 6 months. It's quite doable.
It's not rocket science.
Right, exactly. Well put. Thank you. I'll follow up with you.
Roee, I have a question about the operating system. So what does adjustment to the current operating system that exists on normal PCs have to adjust in order to optimize quantum computing?
I think that's a great question. It's not just the operating system. I think that the challenge, as you go up the stack, you find more and more challenges. For example, the compilers of quantum computers are a very difficult problem. And companies like Microsoft invest today a lot of effort in developing compilers. Other companies do that as well. And then if you go from the compiler, to the higher level, it's not when you run quantum algorithms, you don't run these quantum algorithms using regular computing languages like C or whatever. It's really different logic. Quantum circuits are different. So there are new programming languages that different companies develop today in order to be able to run these quantum computers. So I think if you think about an operating system as an operating system, we're not there yet, but the software layers of the stack, starting from the very bottom, the compiler, all the way up to the programming languages, are now being developed. I think all the big companies like IBM or Amazon or Google or Microsoft have their own versions for a basic quantum computing language. So yeah, it's an exciting period in quantum computing, software-wise as well.
Right, and then if another follow-up question is about the cat. So how do you tame that cat?
So the cat, you're right. I didn't address the cat issue. I said that there's, the quantum mechanics is the physics of atoms and molecules, and I said it's a very different set of laws than the set of laws we use when we think about you, Eli, or me. And that surprised people because we used to think of science as reductionist. We take you, Eli, and we think of you as as a bunch of atoms. And then if these atoms behave in a certain way, why doesn't a bunch of atoms behave this way? And so why is it when you take many atoms, the laws of quantum mechanics sort of fade away, and we start a new operating system, if you like, steps in. And in order to try and exemplify this paradox, Erwin Shcrodinger came with this thought experiment, and he said, look, if I'll put an atom in two different realities, and in one of these realities, the atom would act in a way that would release a poison from a capsule and would kill a cat, I would generate a situation where this cat would be in two different realities at the same time, both being alive and dead. So for Erwin Shcrodinger, this was a proof, if you like, that quantum mechanics is wrong. There's something basic wrong with it. And I think from that moment onward, all the cats of all physicists from that point onward were called Shcrodinger. So that's Shcrodinger cat. And Shcrodinger cat really is a way to highlight this dissonance between the microscopic world and the macroscopic world. What we're trying to do when we try to build a quantum computer is take atoms that behave according to the laws of quantum mechanics, add them one to the other, and then eventually build a large machine, a computer, which can be built eventually from millions and tens of millions of atoms, but still behave according to the laws of quantum mechanics. So if you like, what we're trying to do is engineer Schrodinger's cat. So that's why I call this talk Taming Schrodinger. Bless you.
Bless you.
I have a question.
Yes, please.
Is there a complete, I'm definitely not in this field, so is there complete freedom to collaborate cross-border on quantum projects, or are countries developing regulatory regimes regarding what kind of quantum projects can you cooperate with and with whom?
That's actually a very timely question. When I entered the field of quantum computing, that was in 2003, so 18 years ago. And, you know, it was all about collaboration. It was early days, and scientists are always eager to collaborate. But also government agencies that fund this research had no reason to prevent collaboration. On the contrary, they tried to encourage scientists to collaborate across borders, because it's very clear that if you collaborate, you get more for the buck. So it was a good investment. For the past several years, since quantum computers have become a technology, there's more and more regulation, more and more difficulties on scientists to participate in collaborative projects between nations. There's more and more restrictions on technology being transferred. We just read in it was publicized that the EU is holding, the Parliament of the EU is holding a discussion and a vote in Brussels in a few days from now with a proposal of banning Israel, UK, and Switzerland from participating in quantum programs in Europe. UK, Switzerland, and Israel being non-EU countries that have, are participating in all European research projects, both by chipping in terms of investing in those financially, and in terms of allowing the academics and the industry to compete for these projects. Today, the EU is much more careful, letting technology go from Europe outside. If you ask me, countries are, I think it's too early to build high walls around this technology. I think we're still too early in the technology. I think that much of it is the result of the hype around quantum computing. This field has really exploded in the last 3-4 years, investment-wise and attention-wise. I personally think governments are making a mistake here. I think it'll stall our field. But I think it's an unfortunate consequence, which would be very difficult to avoid, especially taking into account that the world is becoming more and more polarized anyways. If you look at the way US and China are treating quantum information, there's a lot of polarization, and the rest of the world is looking and learning. So yeah, I think it's unfortunate. I wish we could find a better way to deal with that.
Well, I think we have time for one more question. If anybody else has any questions. All right, then we'll go ahead and close. Roee, thank you so much for joining us today and enlightening our Mirage tribe. Highly appreciate it. And thank you all.
There was a person asking a question, Etty Ettinger, but she was unmuted. She was muted, so you couldn't hear, but she was asking a question.
Oh, let me see if we can message her. All right, I asked her to unmute. Let's see.
Oh.
Seems she's muted on her end.
Yeah, she is. I'm trying to unmute her, but she's gotta do it.
Oh, maybe through the chat.
Yeah, let's see. All right.
Can I
Well,
ask another question?
please,
Nika?
please.
So with the maturation of quantum computing, I'm having a hard time imagining whether the implications for modern warfare will be equalizing capabilities or building yet new hierarchies. I'm not sure I'm expressing the question right, but do you understand what I'm saying?
Yeah, yeah. I think, well, I think, you know, I'd like to start by saying that I think quantum computers are not just about warfare. I think like any technology, I mean, look at what the electronic computer did to every aspect of life, right? I mean, these computers were originally built actually for the very, very same motivation. The first electronic computer was built in Bletchley Park as a tool to break the Enigma, the Nazi encryption machine. So actually the motivation in terms of intelligence and defense was actually identical. And these were pretty small and cumbersome computers back then, 70 years ago. But if you look at what electronic computers did to every aspect of our life, from our ability, we were buying encyclopedias 20, 30 years ago. Today, information is it's the cheapest thing on earth. If you look what it did to anything, to science, to our ability to perform logistics, to communicate, to entertainment, and yes, also to defense. We use computers all over. I think a new computing paradigm is likely to be as transformative. It's not just defense, it's really anything. In terms of defense, if quantum computers would be at the hands, it's not easy technology. I think there's very few places in the world where people have the know-how and they're at a sufficiently mature technological level to actually compete and build these things. If quantum computers are at the hands of a few, of course, it builds a hierarchy. It's an advantage. It's a strategic advantage. If quantum computers are everywhere, and that's the way, I think it's a natural course of things for a technology to eventually proliferate, across the globe, then it'll be an equalizer, and hopefully it'll be used to other ends than just defense.
So, but they do neutralize. Let's say the US and China come to it at roughly the same time, they would neutralize the threat of those technologies, right? If I understand correctly. No?
That's right, but I think these are computers. They're not nuclear bombs. So in a sense, they're not threatening anyone through explosions or anything. It's really a matter of whether you can break the encryption of codes. And if your rival has a quantum computer, you better use methods. Actually, the flip side of the coin is that quantum technology gives us the ability to break conventional codes. It also gives us the ability to encrypt in a way which even quantum computers would not be able to break. And in fact, one of the Soyuz moment, if you like, of the US was when it was realized that China was able to send quantum encrypted information in a quantum secure channel to a satellite, which was a global first. And that was 3 or 4 years ago. And then people in the West became a bit worried. So yeah, if you know your rival has quantum computers, you better use quantum encryption in order to protect your secrets.
Thank you.
And it looks like Etty was able to message us, and she's asking, how will quantum computing affect blockchain and Bitcoin, et cetera?
Okay, so both blockchain and Bitcoin is based on blockchain, and blockchain, to the best of my knowledge, uses public key cryptography in a way that it relies on the fact that multiplying large numbers is an easy computational task, but taking a big number and breaking it into the product of prime numbers that compose it is an impossible task for a regular computer if that number is sufficiently large. But for quantum computers, if they're big enough, that would be an easy problem. So blockchain would be breakable given a quantum computer, which would require a new encryption technology for cryptocurrencies. It's not going to happen tomorrow. Don't worry. You don't need to sell your Bitcoins yet.
Well, on that note, I guess we will close. So Roee, thank you once again. And thank you all for joining us. Have a wonderful day.
Thank you very much, Christy. Thank you all. Cheers.
Thank you.